Hello everybody, this is Justin. I'm going to do a physics problem for you. This problem that I'm doing is 16.23 from Mastering Physics. It's actually a pretty simple problem and it won't really take you very long. It's just a matter of being able to manipulate some incredibly simple equations. The problem deals with cell phone signals and how they travel through the air and how they travel through glass. They travel at high frequency HF, and what this question is asking is, say you're in your room behind a 3mm thick sheet of glass, which is your window. How is the frequency and the wavelength of the cell phone signal going to be affected as it travels from the air through the glass into your cell phone? Part A, it's a two-part question, is going to ask what the frequency is when it goes through the glass to your room. So the relevant equations that we're going to use for this problem, we're going to use the lambda times frequency equals the speed of light. Lambda times frequency equals velocity. If you remember that, we did a lab using the computer one Tuesday a while ago. Also, we're going to use that the velocity of the wave through the glass is going to be the ratio of the speed of light to the n value, which is your refractive index of glass. The knowns in this problem, it gives you that the wavelength initially through the air of the cell phone signal is 35.3 centimeters. The speed of light is a constant. It's 3 times 10 to the 8th meters per second. And the refractive index of glass, if you remember back from the light ray portion of our class, it's going to be 1.5. Part A, what is the frequency when the signal travels through the glass and gets to your room? So basically with that, we're going to rearrange the lambda times frequency equals the speed of light equation to solve for frequency. The speed of light over lambda, 3 times 10 to the 8th meters per second divided by 0.353 meters. Now this is going to be the same when it's going through the air, and it's going to be the same going through the glass, and it's going to be the same in your room. And the reason for that is because the frequency is actually set by the source of the wave, and it doesn't change going through the mediums. So your frequency through the air is going to be the same frequency through the glass. So that's going to be the answer for A. It's a real quick calculation. Now part B asks what happens when you what happens to the wavelength going through the glass. Now this does change going through the medium. The wave is actually going to slow down as it goes through the glass. And to calculate that, you need that the refractive index of glass, the n value, is going to be 1.5. So we'll change that to a fraction to make it 3/2. Using the earlier equation, the velocity going through the glass is the speed of light divided by the refractive index. You get that it's c divided by 3/2. That's going to be the same as saying 2/3 times the speed of light. Now your initial wavelength is 35.3 centimeters, so we'll do some equation arranging here and solve for lambda. Lambda is the velocity over the frequency, which equates out to 2/3 speed of light divided by the frequency. But this is also the same as saying it's 2/3 of the wavelength through the air. Once you have that equation, it's super simple. You just take 2/3 of your 35.3 centimeters, and that comes out to 23.3 centimeters. So that's saying that when the signal goes through the glass, it actually compresses and makes a shorter wavelength, despite the fact that the frequency is not changing. So that was a pretty simple problem, and it really shouldn't take you very long if you just can handle the simple equations and get your knowns right. Once you have all the knowns and everything, then this will take you about 5 minutes. Alright, thanks for watching.